The cosmic cycle, exploring black holes as progenitors of universal genesis. Introduction. The origin of our universe, commonly referred to as the Big Bang, represents one of the most profound questions in cosmology. While the standard inflationary Big Bang model has substantial observational support, the pre-inflationary conditions remain largely speculative. This paper explores a cyclical cosmological framework wherein supermassive black holes may serve as potential seeds for subsequent universal genesis events. Theoretical framework. Current cosmological models typically describe a universe with a definite beginning, the Big Bang, occurring approximately 13.8 billion years ago. However, this paradigm invites a natural question: what preceded this event? The concept of a singular beginning presents philosophical challenges regarding causality and initial conditions. Hakulta, a cyclical cosmological model, offers an alternative framework that potentially addresses these concerns. Rather than positing a singular creation event, such models propose that our universe may represent one iteration in an infinite series of cosmic cycles. Black holes as universal progenitors. Supermassive black holes, SMBHs, present intriguing candidates as seeds for subsequent universal iterations. As these objects accumulate mass over cosmological timescales, they could eventually reach extraordinary scales, potentially accreting matter equivalent to trillions of solar masses in the far future of our universe. The mechanism by which such objects might initiate a new cosmic cycle could involve several theoretical pathways. 1. The Big Rip and the end of time. The Big Rip is a hypothetical cosmological event in which dark energy, instead of remaining constant as in a cosmological constant, increases in strength over time. This acceleration would eventually tear apart galaxies, stars, planets, atoms, and even space-time itself. In this scenario, at the end of time, space is completely destroyed, except within supermassive black holes. These black holes survive because their gravitational singularities cause space itself to condense within them, meaning that while space is gone outside, they retain an internal pocket of space. 2. Supermassive black holes detached from space. With no surrounding space, the black hole is no longer interacting with the normal structure of space-time. The event horizon remains, but there is no external reference frame to compare with. Since black holes warp time and space, being detached from normal spacetime could mean infinite frame dragging. Faster than light, FTL, rotational speeds due to extreme spacetime warping. Faster than light, rotation. Normally, relativity prevents objects from exceeding the speed of light. However, in Kerr black holes, rotating black holes, the region within the ergosphere can exhibit superluminal effects due to extreme frame dragging. If detached from external spacetime, the black hole could, in a sense, rotate infinitely fast without violating relativity because there's no external observer to measure it against. 3. A new form of time and space generation. With black holes persisting beyond the Big Rip, they enter a new time separate from the previous universe. In this time, their rotation and quantum effects release a new space fabric into the future, essentially recreating a new spacetime continuum. How does this new space emerge? Black holes contain extreme energy and mass, and their disconnection from normal spacetime could allow energy to be released in novel ways. The faster-than-light rotation could lead to quantum fluctuations that produce spacetime, similar to how virtual particles emerge in quantum field theory. 4. Black hole mass loss and the transition to a Big Bang. Over time, the black holes start losing mass as they radiate energy into the newly forming space. This process could resemble Hawking radiation on an extreme scale. As mass is lost, the event horizon shrinks, increasing the instability of the black hole. At some critical point, the black hole becomes unstable and explodes, releasing all its condensed energy. This explosion serves as the new Big Bang, generating a new universe from the remnants of the old one. 5. Implications for cyclic universes. This model implies a cyclic cosmology where each universe eventually ends in a Big Rip. Isolated black holes transition into a new era of time. Their faster-than-light rotation seeds the next Big Bang. A new universe emerges, potentially with different physical laws. This model resolves some paradoxes. It provides a natural mechanism for cosmic rebirth. Unlike a heat death, where everything fades into an entropic void, black holes become the bridges between universes. It explains why time continues despite the end of space. The existence of supermassive black holes ensures time and energy persist beyond the Big Rip. He wants it Kargap. It suggests that black holes may be the source of fundamental spacetime. Instead of just consuming matter, black holes might generate new spacetime, making them essential to cosmic evolution. Quantum tunneling. At extreme densities, quantum mechanical effects may become significant even at macroscopic scales. A sufficiently massive black hole might undergo a quantum tunneling event, effectively evaporating into a new spatial configuration. Spacetime topology transformation. The extreme curvature within SMBHs might induce fundamental changes in spacetime topology, potentially creating a bridge to a new cosmological domain. Information preservation mechanism. If information is preserved rather than destroyed in black holes, as suggested by quantum information theory, this might necessitate a mechanism for information release through a new expansion phase. Singularity bounce. Theoretical physics suggests that at the singularity of a black hole, where current physical laws break down, a bounce might occur, initiating expansion rather than continued contraction. Implications and observations. This cyclical model has several implications for our understanding of cosmology. 1. It addresses the metaphysical challenge of an absolute beginning by suggesting a potentially infinite series of cosmic cycles. It provides a naturalistic mechanism for universal genesis that emerges from established physical entities. It suggests that fundamental physical constants might exhibit subtle evolutionary changes across cosmic cycles. It proposes that information from previous universal iterations might be encoded in the structure of subsequent universes. Conclusion. While speculative, the concept of supermassive black holes serving as seeds for subsequent universal iterations offers a compelling framework for addressing fundamental questions about cosmic origins. This model suggests that rather than a singular beginning or end, our universe may represent one iteration in an infinite cosmic cycle, a perspective that aligns with both philosophical principles of continuity and emerging theoretical models in quantum gravity. Further investigation of this hypothesis will require advances in our understanding of physics at extreme energy scales and potentially observable signatures of previous cosmic cycles in the cosmic microwave background radiation or other cosmological data.